Imagine giving an LLM a 500-page technical manual and asking a single question. Even today's largest context windows of LLMs have practical limits. Sending a whole document increases cost, latency, and often reduces answer quality because irrelevant information overwhelms the useful parts. Retrieval systems solve this by breaking documents into smaller pieces called chunks. But where should those chunks begin and end? Surprisingly, that decision has a major impact on the final answer quality. During ingestion in the vector stores, enterprise documents are rarely stored as one giant block. PDFs, manuals, wiki pages, emails, and documentation are divided into smaller sections before embeddings are generated. Each chunk receives its own embedding and metadata before being stored in a vector database. Later, retrieval happens at the chunk level, not the document level. This allows the system to retrieve only the most relevant portions instead of entire documents. The most straightforward approach is fixed-size chunking. Every document is divided into equal token windows, for example 512 or 1024 tokens each. This approach is simple, predictable, and fast. However, fixed boundaries often cut through paragraphs, code blocks, tables, or explanations. Important context may be split across multiple chunks, making retrieval less accurate even though every piece was indexed correctly. To reduce information loss, production systems usually introduce overlap between consecutive chunks. Instead of creating chunk 1 and chunk 2 independently, the second chunk repeats part of the previous one, perhaps 100 or 200 tokens. This repeated context helps preserve relationships that span chunk boundaries. Although overlap increases storage requirements because some text is duplicated, retrieval quality often improves significantly. Fixed token windows ignore document structure. Semantic chunking instead attempts to split where ideas naturally change. Headings, paragraphs, sections, code functions, markdown headers, API endpoints, or topic transitions become chunk boundaries. The resulting chunks are more coherent because each represents one complete concept. Better semantic coherence usually produces better embeddings and more accurate retrieval. Chunk size is always a trade-off. Small chunks improve retrieval precision because each embedding represents a focused idea. However, very small chunks may lose surrounding context. Large chunks preserve more context, but dilute the embedding because multiple topics become mixed together. Production systems balance these competing goals based on document type, query complexity, latency requirements, and the capabilities of the embedding model. Every chunk is typically stored alongside metadata, such as the source document, page number, section heading, permissions, timestamps, document type, language, or author. Some systems also maintain parent-child relationships so that once a relevant chunk is retrieved, the application can expand outward and recover additional neighboring context before sending information to the LLM. This improves answer completeness while keeping retrieval efficient. So, during inference, the user submits a question. The query is converted into an embedding and compared against stored chunk embeddings. Hybrid retrieval, filters, and re-ranking operate on these chunks rather than on entire documents. Only the highest-ranking chunks are finally assembled into the prompt. The LLM never reads the entire knowledge base. It reasons only over the carefully selected evidence returned by the retrieval pipeline. Chunking is much more than splitting text into smaller pieces. It determines the quality of embeddings, retrieval accuracy, token efficiency, and ultimately the quality of answers produced by the LLM. Fixed chunking emphasizes simplicity. Overlapping chunking preserves context, and semantic chunking preserves meaning. If you remember one thing from this video, remember this. Better chunks create better retrieval, and better retrieval creates better AI answers. Hope you enjoyed the sketch. We'll see you in the next one.